we were talking about the Schrodinger equation and how we take the energy that an electron has, we put that energy into the Schrodinger equation, and we can determine where those electrons are in an atom. Okay? And so electron energy goes in, and the way we describe the energy the electron has is with these quantum numbers. Okay, so you put these quantum numbers into the Schrodinger equation, and you get a probability map. So, a probability of where those electrons can be. And we call those electrons orbitals, or we call those probability maps orbitals. Okay, and so we talked about the rules for the quantum numbers, right? We've got n, which is the energy level. We have L, which is the shape, M sub L, which is the orientation, and M sub S, which is the spin. Okay, so there's those 4 quantum numbers, which is like an address kind of where those electrons can exist. Now, what I want to do is kind of look at those rules of what those numbers can be and list all of the possible combinations for an electron that has an energy of n equals 3. Okay, I'm going to go to the next slide, and we want to start with what happens if n equals 3. Okay, so if n equals 3, then my L values can equal all of the integers up to n minus 1. Okay, so we start with 0. It can be 1, and it can be 2. Okay, so I kind of got these spaced out. So if n equals 3, then my L value can be 0, it can be 1, and it can be 2. Now remember, these L values correspond to a letter, right? So if my L is 0, then the energy level 3, n equals 3, and 0 is an S, okay? If my L equals 1, it's a P, and if we're in energy level 3, then it's 3P, and 2 is D, and that energy level is 3, okay? So these are all just kind of reminders. So now if I look, my next letter is M sub L. Okay, and if my number is M sub L, remember it can equal L to negative L. So if L equals 0, M sub L has to equal 0. If L equals 1, then M sub L can equal negative 1, 0, or 1. Okay, and if L equals 2, then M sub L could equal negative 2, negative 1, 0, 1, or 2. Okay. If your M sub L number is negative, then it's just the negative number. It doesn't mean a deficit. It just means a direction. Remember how, like with energy, a negative energy meant it was going out of the system. Yeah, negative is out. So same thing here. It's just kind of a direction. And so remember, M sub L is the orientation, right? So if we have 0, S can only have one orientation. So again, this is the 3s orbital. P's can have 3 different orientations. So we have a px, a py, and a pz, right? So px is that lobe on the x-axis, py is the y-axis, and z is up and down. Okay, so that's what those numbers mean, is the orientation or the axis that the orbitals are on. Okay, and then there's 5d orbitals. So there's the dxy, dyz, dxz, dx squared minus y squared, and dz squared. Okay, and so you guys know those pictures, right? They're just different, they're just pointing different directions. And so then remember, for m sub s, we can have a +1/2 or a -1/2, right? So for every single one of these orbitals, I can have a +1/2 or a -1/2. So each one of these. So there's a lot of different possibilities of where an electron can exist if it has an energy of n = 3. Now, what we do as chemists, instead of writing out these quantum numbers, we have a shortcut that we draw, okay? And so what I do for the shortcut is for every orbital I have, I draw a box, okay? And if my electron has a +1/2, I draw an up arrow. And if it has a negative, I draw a down arrow. So this one box right here represents the 3s orbital with 2 electrons, one that spins up and one that spins down. Okay. Now the p orbitals, there's 3 of them, the px, the py, and the pz. And since they're all the same orbital, but the direction's different, what I do is I draw these 3 boxes together. Okay, so here's the 3p orbital with a px, py, pz. And I can put an electron with a positive spin or an electron with a negative spin. Okay, so in the 3p orbitals, there can be 6 different electrons. And then same thing with the d, they're all the same orbital, just a different orientation. Well, I should say they have the same orbital energy. And this time, because there's 5 of them, I draw 5 boxes. And in every box, remember, each one represents an orbital. And in an orbital, you can have only 2 electrons. So we'll draw all of our electrons in. Okay, so each box represents an orbital. And remember, an orbital is where an electron can exist in an atom. And in an orbital, we can only have 2 electrons. Okay, so we use these boxes as a shorthand notation. Any questions about that? Okay. So I wanted to show you the shapes, right? So here's my s orbital. It has a box, and I can put 2 electrons in that box. One has to be +1/2, one has to be -1/2. Here's my p orbitals, the px, the py, the pz. These are the exact same energy, they're just on different planes. So that's where the 3 boxes come from, right? And in each one of these orbitals, I can have a +1/2 and a -1/2. Okay, and then here's my 5d orbitals. Those are big boxes. And so here's my dx squared minus y squared. See how the lobes are right on the xy axis? And this orbital right here can have 2 electrons in it. And I can put those electrons anywhere, right? This is a probability map where if at one time I like froze the atom, there would be 2 electrons somewhere, most likely in this space. Okay. And so that's what each one of these represents. Okay, so I had a great question. So the question was, if there's 1 orbital per box, then how come there's 2 different lobes or 2 different balls, right? So this right here represents 1 orbital. So a lot of times you'll see it drawn like this, where they're kind of connected. But remember, As you increase energy, you have nodes, right? And so a p orbital is higher energy, so there has to be a node where electrons can't exist. And that node is this angular node that's in the middle. So in a p orbital, I can have one electron on this side and one electron on that side, or I can have two electrons on one side or two electrons on the other side. They just can't exist in this middle node section. Okay, so that shape is one orbital and the electrons can go back and forth. Same thing here, there's 4 different shapes, but only 2 electrons can exist in this area. They can be in the same lobe, they can be in opposite lobes, they can be next to each other in the lobe, but this is kind of the shape that they can exist in or move in, okay? And the question is, can they pass through a node? Yeah, so they can go back and forth in here. Remember, their electrons don't stop. I don't even know if they stop at absolute zero. So if absolute zero is 0 Kelvin, which is super, super cold, and you kind of freeze everything, so you might be able to get electrons to stop. But otherwise, they're just moving around so fast in this area that at any given time, if you stop if you freeze them, they'll be in that area. So yeah, they can pass through the nodes. And just like with the energy levels, remember, they can jump up into different energy levels too. So they're always kind of moving. They just, depending on how much energy they have, they like to be in a specific area. Another question is about these arrows. So yeah, every single arrow is an electron, right? So if I have the up, it means that electron has a positive 1/2 spin, and the down one means it has a negative 1/2 spin. You don't have to worry about the number 1/2, positive 1/2, negative 1/2. Just, you can only have like a positive and a negative 1/2 in a box. Okay, so since we can put these electrons into orbitals, right? Into these boxes or into these shapes. So here's a 1s orbital box or the 1s orbital shape, right? So this is the representation of 2 electrons in this orbital shape. There's rules that we have to put electrons into these orbitals. Okay, there's the Pauli exclusion principle, there's Aufbau principle, and there's Hund's rule. Okay, and these 3 rules or principles are what we use to decide where electrons can exist in those orbitals. Okay. Let you look at that for a second. There was a question that came to me through the question and answers. I'm not sure what your question means. So maybe as I explain and we go through, you'll be able to understand a little bit, but keep asking me questions, you guys. I want to make sure that you understand this stuff. Okay, so the Pauli exclusion principle says that no 2 electrons can have the same 4 quantum numbers, right? And we talked about that. It's like seats on an airplane. You can't have 2 people in one seat. They have to have different seat numbers, okay? And so we can have 2 people in the same row, right? So I can have 2 electrons in an orbital, 2 people in the same row, but I can't have 2 electrons in the same seat. Okay, so no 2 electrons can have the same 4 quantum numbers, and that means a maximum of 2 electrons can be in an orbital. And it works out that if you do this, then the quantum numbers are different. Okay, the next rule is Aufbau principle. And this says that electrons fill lower energy levels first. Okay, and so the ground state is the very, very lowest energy state. So ground state usually means n equals 1, right? So n is the lowest energy state. And then after that ground state, it's going to fill n equals 2, n equals 3, etc. Okay, so we want those electrons to fill the lowest energy levels first. This word right here, Aufbau, is German for building up. And so it's saying, okay, you got to fill the lower energy levels first. And then we have the last rule, which is Hund's rule. And Hund's rule says, when filling degenerate orbitals, and degenerate means they have the same energy, electrons fill each orbital before pairing. Okay, so what that means is I have a p orbital, right? And that p orbital can be a px, a py, or a pz. So if I have electrons, okay, all these three p orbitals are the same energy. So when I fill electrons, what I do is if I have 4 electrons to put into this, into these boxes, I take and I fill 1, 2, 3. So I fill each orbital and then I pair them. 4. Okay. So in these p orbitals, there's 4 different electrons. So degenerate orbitals mean like all the 2p or I don't want to say that. I'll explain that as I go. Oops, my eraser's not working. So degenerate is when you have boxes that connect each other, right? That's when you fill all the orbitals first and then you pair them. Okay, so let's do an example of this. And so those are my 3 rules. And so the way that I can easily kind of think about where the electrons are is I'm going to use the periodic table. Okay, so remember we've got our energy levels here. Okay, so this line right here is my first energy level. And I've got my second, third, fourth. Okay, now in this, these first 2 represent my s orbitals. Okay, and s orbitals can have 2 electrons. And there's 2 boxes. Okay, these represent my d's. There's 5 orbitals, and so there's actually 10 boxes right here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And then here's my p orbitals, and there's 3 orbitals. And there's 1, 2, 3, 4, 5, 6. Okay. And then my f orbitals down here, there's 14, and there's 7 orbitals. So we can actually use the periodic table to kind of figure out where those electrons go as we build up the atoms and the electrons. Okay. And so remember, as we're adding electrons into the orbitals, I'm going to go back for a second. We have to follow these rules, because if we follow those rules, it makes all of the electrons happy, all of the atoms happy, right? So we can't put more than 2 electrons per orbital. We have to build from the ground up. So we start at n equals 1 and build up from there. And then we use Hund's rule to say, okay, when we're filling these orbitals in, I have to fill each orbital that's degenerate or the same energy before I start pairing those charges or those electrons. Okay, so we got to follow those 3 rules. So let's kind of look at, one more thing I want to show you guys is I added this table for you guys, and it's a periodic table, and it kind of goes through and shows what orbital is being filled where. So here's the 1s orbital, and then the 2s orbital, and then the 2p, because remember, these are my energy levels, n equals 1, n equals 2, n equals 3. So 3s, 3p. Then we have 4s, and then here's 3d, right? So the 3d orbitals are just not in the right line or the right column, or not column, but row, sorry, not the right row, okay? So then 5s, 4d, 5p, 6s, and we go to the 4f, 5d, 6p. Okay, so we're going from the bottom, and depending on the number of electrons, we build up from the bottom. So if I look at hydrogen, okay, hydrogen has 1 proton, and because it has a neutral charge, it has 1 electron. Okay, so I'm going to start right here, and if it has 1 electron, then it's in this first row right here. My energy level is 1. I have an s, because that's the orbital that it fills, and in that s orbital, there's 1 electron. Okay, so this is called an electron configuration. Okay, electron configuration has this 1, which is the energy level. Level. S is the orbital. And this little number up here is the number of electrons. Okay, so hydrogen that has 1 electron, I start up here in energy level 1. The orbital is S, and because there's only 1 electron, that's the number of electrons. Now, if I use the box notation to draw this out, I draw a box. I say this box is the 1s orbital, and there's 1 electron in it. Okay, and I just preferentially put the positive first, but you can also do the negative one first. It doesn't matter, okay? You just have to have 1 electron in that orbital. You guys still okay? Okay. Yeah, so I am going to post these after class. So you get my blank PowerPoint slides and my PowerPoint slides with the letters, the writing in them. Okay, so let's look at fluorine. Okay, so what I do is I find it on the periodic table, and it's down here at the bottom. Let's do orange. So it's right here. Okay, if it's neutral, that number 9 right there is the number of protons, but it's also the number of electrons. Okay, so fluorine has 9 electrons in it. Now those 9 electrons, what I have to do is I have to start from the ground level or the bottom and build my way up, right? That's the off-bow principle. And so when I'm looking at these electrons, I'm going to start right here. Okay, because I've got to start at the bottom and build my way up. So the first orbital that I come across is the 1s orbital. Okay, and if I go through and kind of count those boxes, right, there's 1, 2 boxes. I'm going to draw my F right there. Okay, so very, very first, I'm building up. I have fluorine. I go 1s and 1s, and there's 2 electrons. Then I go to the next line. And this next line is the 2s orbital. Okay, so I have the 2s orbital, and I have 1, 2 boxes in that, so I put 2. So I'm using the periodic table to kind of keep track of the levels or the energy levels of where my electrons are at. Okay, next I go all the way across the periodic table, and I hit the 2p orbital. Okay, that 2p orbital has 1, 2, 3, 4, 5. And when I get to 5, I get to my element. So this is 2p5, because as soon as you get to your element, you stop. Okay, and if you look, I have 2 electrons plus 2 electrons is 4 electrons plus 5 electrons is 9 electrons, right? So 2, 4, so this is my electron configuration for fluorine. It tells me exactly where my electrons are at in that orbital. Okay, now if I want to go through and draw the box notation of this, right? I take and I draw a 1s orbital. I draw a 2s orbital. And I draw the 2p orbital, but remember the p's can be px, py, or pz. And then I go through and I put my electrons in each of these boxes. So this has 2. So I have a positive 1/2 and a negative 1/2. This orbital has 2, a positive 1/2, a negative 1/2. This has 5. And now remember with Hund's rule, when I'm filling these electrons, I have to put 1 in each of these boxes first, and then I can go back and pair the electrons. Okay, so just some like vocabulary with this. This notation is called the SPDF condensed. Configuration. Okay. This is called the orbital diagram notation. Okay, so what it does is, if I just say, what's the electron configuration, then you can write any of these. If I say, what is the condensed notation, you can write this. Another notation, we're going to draw this one in green, is to be more specific. Okay, so right now I'm just telling you that there's 5 electrons in the p orbital, but I can be more specific and tell you exactly what orbital these electrons are in. Okay, so if I do that, then I have a 1s with 2 electrons. I have a 2s with 2 electrons. I have a 2px that has 2 electrons. I have a 2py with 2 electrons. And I have a 2pz with 1 electron. Okay, so if I do this, this is called the SPDF expanded notation or electron configuration. And so each one of these, this gives me a more specific description of where those electrons can be in an atom. Okay. Any questions about this? So the question was about this p orbital, and says, why are we using x, y, and z? And how would we use it with more boxes? Remember, each one of these boxes represents an actual orbital. So the px orbital is this barbell shape along the x-axis. So there can only be 3 p boxes because there's only 3 p orbitals that are in those different orientations, right? The pz is that shape along the x-axis. Okay, there's no other boxes with p. With p, you can only have those 3 boxes because you can only have 6 electrons. And once those are full, then you have to move on to the next energy level or the next orbital. Okay. Yeah, so let's go to, I want to talk about this for a second, and then we'll do a couple of more examples. So this is just kind of a little thing that says indicate whether the configuration, so this is the orbital box configuration, right? So configuration just means arrangement or where the electrons are at. Which do these correspond to the ground state or an excited state? Okay, and so you'll hear these words. So ground state means all of the rules are followed. So is the Aufbau principle, is the Hund's rule, is what's the other one? Pauli exclusion principle. Are all of those followed? Okay, and so boron has 1, 2, 3, 4, 5 different electrons. Okay, and if this was in the ground state, then all of the rules would be followed. Now, if it's an excited state, that means there's added energy. Okay, and so if we just add a little bit of energy to an atom, then it allows the rules to be broken. Okay, so let's look at this first one. So boron has 1, 2, 3, 4, 5 electrons. Is this one in the ground state or the excited state? Okay, there's a few answers coming in. Okay, so most people are telling me excited. How come this is in the excited state? A couple of ground state. Why is this excited? Right, so here we didn't fully fill this box. Okay, so if we didn't fill the box, let me go back to my. So remember, if we're using the Aufbau principle, make sure I spell it right. AUFBAU. So the Aufbau principle says we have to fill from the bottom up, right? And so because this electron is here instead of here, it's an excited state. So you guys are right. So they're not filling in properly. They're breaking the law. I like that. It's a law breaker. The Aufbau principle is broken. So what happens is if you have all of these in the ground state and you add energy, the electron can move up to a different orbital. Remember, and that's what we saw with the emission spectra or the absorption spectra. Electrons can move if they have energy, and if they have that extra energy, then they're in the excited state. Okay, so what about this one? Carbon. So carbon has 6 electrons. Is this excited or ground state? Okay, so I'm seeing a lot of grounds and a lot of exciteds. Okay, so with this one, I'm going to say excited. Okay, and the reason is the reason that it is excited is because when I fill these boxes, the first thing I want to do is fill all of them with the same spin. Okay, and so because this one's flipped, it violates Hund's rule. Okay, so remember with this one, I want to fill the boxes like this first before I start pairing. Okay. Okay, so now what about nitrogen? Nitrogen has 1 more electron. So now we're at 7 electrons. Okay. See lots of people writing ground. So why is it the ground state? Because it follows all the rules. right? You guys are fast typers. So my s orbital is full, then my 2s orbital is full, and then here's my p, right? 1, 2, 3, they're all the same direction, okay? If I were to add another electron, then I can start pairing. But I have to have all those boxes have the same spin first. Okay, so that's why this breaks the rules, because we have one up and one down, and this one follows the rules because it has all of the same direction first before we add the next one. Okay, now we've got oxygen. Oxygen has 8 electrons. Is this excited or ground state? Okay, so lots of excited. I see you guys are getting good at this. Okay, so why is this excited? Because I have to fill all of the boxes first. Okay, so the ground state would take and go 1, 2, 3, and then pair. Okay. So when all these boxes are the same, they're degenerate. Or, you know, like when I draw these 3 boxes in one, they're degenerate, which means I have to fill all the boxes before I start pairing them. Okay. And so this is another Hund's rule violation. Okay, and so notice you guys, like, as we're adding electrons, we got 5, 6, 7, 8. All of these kind of stay the same, right? I go 1s, 2s, 2p, 1s, 2s, 2p. And so they fill in that same order, okay? So one of the questions was, do we have to put the spin up in the boxes with one arrow? So you have to keep the arrows consistent. So like with this carbon right here, what I could do is draw these 2 arrows down, and that would be okay too. Okay, so either of those are okay, but I just can't have one up and one down in these degenerate orbitals, right? The orbitals with the same energy. Okay, let's see what other one more question came in. So why would opposite arrows be a violation? So it's not like it's a violation in the fact that it needs a little bit more energy in order for this to happen. Okay, so it's not that it's not possible. It's possible. It just has a little bit of extra energy in there. Okay, so the ground state is everything's at the very lowest energy possible, right? But when those electrons flip or whatever, I need to add energy in order for it to happen. Okay. So same thing here, because it violates the rule. It can happen. It just means that there's energy that's been added to that atom in order for it to happen. Okay, so I think I have a couple more examples. This time we're getting a little bit bigger. So write electron configurations. Using different notations for strontium. Okay, so first thing we do is we look at the periodic table and we're looking around to find strontium, and we find it down here. Okay, so strontium has 38 electrons. And so I'm going to start at the bottom and build up from there. Okay, so strontium, first thing I have to do is fill that 1s orbital. And that 1s orbital has 1, 2 electrons. Next, I go to the next level and I'm at the 2s orbital. Okay, in that orbital, there's 1, 2 boxes. Next, I go all the way across here to the 2p orbital. And that 2p orbital has 1, 2, 3, 4, 5, 6. And then I go down to the 3s orbital. So I'm just using the periodic table to kind of help me build up, right? Because I have to build up from the bottom up to the strontium down here. So here we've got 1, 2. Let me go across here to 3p. And 3p has 1, 2, 3, 4, 5, 6. Next we go here to 4s. That has 1, 2. Okay, now we hit the Ds, right? When we hit the Ds, we're at 3D. And 3D has 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. There's 10 electrons in that 3D orbital. Now we're at 4p. 1, 2, 3, 4, 5, 6. And now we go here to 5s. And there's 1, and we get to our element we're looking for, 2. Okay, so all of these elements are going to build up. So strontium, the noble gas configuration is 1s2, 2s2, 2p, or sorry, not the noble gas configuration, but the SPDF configuration is 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6, 5s2. Okay, and so that's like a lot to write out. And so one of the things, so there's a question before I finish this. Why do I go 3s, 3p, 4s, 3d, 4p? So this is just the way the energy levels work, right? So these are based on the quantum numbers and the shape. And so as we get further and further up away from the nucleus, then these orbitals get really, really close in energy. And so it just so happens that these ones are in the 3D. Okay, and then notice that they're kind of off all the way down. So 3D, 4D, 5D. Okay, so they're all based on that orbital energy. If you wrote those two in different orders, it's okay. I just like to write it in this order because it follows the periodic table. Okay, so then I wrote up here condensed noble gas notation, right? So there's a shortcut where we can go through and do this. And so let's do the shortcut. Okay, so as I'm building up these these electrons in this atom, right? I know that if I get to krypton, I'm just going to write it here. So if I get all the way up to krypton, it's going to have this configuration that's 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3pd, 4p6, right? So krypton has that electron configuration. So if I say, well, strontium is krypton plus 5s2, then instead of writing everything out, I've shorthanded it, right? So krypton is this whole electron configuration with my 36 electrons. And strontium has 2 extra electrons. So strontium is krypton plus 5s2. Okay, and so this is called the condensed noble gas notation, right? Because I'm using the noble gas to tell you kind of the last shell or energy level that the electrons fill plus whatever's left over. Okay, so if I use that notation, I have to use a noble gas. and then add whatever's left over. Okay. So when I look at this, right, all of these electrons are what's called core electrons. These core electrons are on the inside of the atom. They're all of the electrons that aren't in the outer shell, okay? And the shell is those energy levels. So 1s is closest to the nucleus. Then we move out to 2s and 2p, which is further from the nucleus. And then the 3s are further from the nucleus, and the 4s are even further. And then we hit 5, right? And 5 in this atom is what's called valence electrons. And valence electrons are the outer shell. Or the highest number. So in this case, the highest number is 5. And so my outer shell or my valence electrons are 5. Okay, any questions about that? So up here I have, whoops. So I have my condensed SPDF, and down here I have my noble gas notation, right? I'm shorthanding, so I don't have to write every single thing out. Yeah, so someone asked me about krypton. If we're just looking at this, then valence electron. So, what's krypton's valence electrons? The valence electrons are the ones that are in the outer shell. And so for krypton, the outer shell would be the 4s, right? And so 4s2, 4p. So in krypton, there would be 8 valence electrons. Okay, you're just looking for the highest number. Any other questions on this? I kind of just dove right in and did a really big one. Okay, now I want to show you guys, so there's also ions that we can write electron configurations for, right? And so this right here is strontium 2+. And so there's a couple ways you can do this. One of the ways is to take strontium, and if we take and lose 2 electrons, then we get strontium 2+. Okay, so I'm just going to write that out. And so one of the things that I can do is write the electron configuration for strontium. Okay, and if we do that, remember here's strontium right here. And so I'm going to use the noble gas notation or that diagram. And so I go back to krypton. Okay, so whatever element I'm given, I go back to the noble gas that it's at. And then I add the next electrons, right? So krypton 5s2. So now if I take this strontium and I remove 2 electrons, then I get strontium 2+. Okay, and so strontium 2+ means I take and remove these electrons. So the noble gas configuration of strontium 2+ is actually the same as krypton. Okay, These are called isoelectronic. It means they have the same electron configuration. Okay, so we removed those valence electrons and we're left with, whoops, this krypton. Okay. So there's a question, can strontium be 3+? So that would mean I would have to take one more electron. So here's the other way I can do it, right? If I have strontium 3+, I start with strontium, I'm losing 3 electrons. I lose 1, 2, 3 electrons. And so it's going to be the same configuration as bromine. Okay, so now if I do this, to do the orbital diagram or the shorthand, I go back to the last noble gas, which is argon. And then I fill in my the rest of my orbitals or my electrons. So 4s2, 3d10, 4p, 1, 2, 3, 4, 5. Okay, so you can just keep removing electrons and writing it out. So remember that this argon is just a shorthand. It just tells you like, hey, I'm lazy and I don't want to write all these letters out, right? And numbers. So everything up to argon plus whatever's left over. So now we've got these valence electrons and we've got new core electrons. But this doesn't really exist because it's really, really hard to remove core electrons. Okay, and so we'll talk about that more in chapter 9 as we get to it. So valence electrons are pretty easy to remove, but those core electrons are hard to remove, right? Because they're near the nucleus. Okay, I think I have another example for you guys. Oxygen 2-, right? So oxygen plus 2 electrons goes to oxygen 2-, right? So if I look here, we've got oxygen right here. And I don't know, I kind of like to think of it as the neutral atom first, and then I add my extra electrons in. So I have 1s2, 2s2, 2p, 1, 2, 3, 4. Okay, now if I draw the orbital box notation of this, it looks like that, where this is 1s, 2s, 2p. So I put 2 electrons in my s, I put 2 electrons here, and then in my p orbital, I put 1, 2, 3, 4, following all of the rules, right? So this is oxygen. Now for this reaction, or for me to get oxygen 2-, I have to add 2 electrons. And notice there's 2 spaces here in this orbital. So I'm going to take and add those 2 electrons in this orbital. So I add 1, 2. Okay, and so when I do that, I add those electrons, it becomes oxygen 2-. So now for oxygen 2-, it's 1s2, 2s2, 2p6. Okay, so I use the different notations to kind of help me keep track of those electrons and where they get added. And so if you write this out, you can always write out the orbital box notation to kind of help you. Okay, any questions about that? So question, can I just put in neon? Yeah, so if I have O2 minus, it's isoelectronic or has the same electron configuration as neon. So that's another way. I start with my oxygen, I add 2 electrons, and I get to neon. Yep, so either of those is correct. Any other questions? Okay, so there's just a few like kind of little vocabulary words. Oh, next we'll do uranium. Okay. And so I just wanted to show you guys, like as you increase levels of the periodic table, the energy levels get close together. Okay, so uranium is clear down here, right? Uranium is an F block element. And those F block elements go right up here and the periodic table expands. Okay, and so notice as you get down here, instead of following the regular trends, and I guess I should just show you like, so with hydrogen here, we've got 1s. So this periodic table shows you the last electron that goes in, right? So 1s1, 1s2, 2s1, 2s2, 2s2, 2p1, 2s2, 2p2. So it goes through and it tells you what the electron configuration is. Okay, but only for those outer elements. So for this argon right here, it's like neon 3s2, 3p6. Okay, and so all of these follow that Hund's rule or the off-bow principle of us moving up. But as we increase energy levels, the energy levels get closer together. And so they kind of stop following the rules. Okay, so if I have the electron configuration for uranium, right, you would expect it to be right down here at the bottom, you'd expect it to be this Rn configuration. And then we go here to 7s2. And then notice that like the 60s come in. So 61, and then 1, 2, 3, 5f3. Okay, and so uranium actually is that 7s2, 5f3, 61, right? But this D right here is in there because those energy levels get really, really close together. And so as we go down the periodic table, like it kind of stops following the rules and the 6D comes in when it really kind of shouldn't with the Fs. And like, you know, this element right here, PA goes 7s2, 5f2, 61. And so down here, the F block elements kind of stop following the rules. And so I put this periodic table in here for you guys to use, just so you can kind of see like where the weird electron configurations are as you increase the levels. Okay, and it's all because those energy levels get really close together, and so the electrons can be in different orbitals without sacrificing the amount of energy that they have. And so that periodic table will be available for you too. Okay, and so the kind of the last things I want to talk about, this is kind of starting at chapter 9, and just the idea that the chemical properties of elements, so how they behave, are determined by the valence electrons. And so here I have chlorine, and the electron configuration of chlorine is neon. So down here, 3s2, 3p, 1, 2, 3, 4, 5, right? So there's chlorine. And so the way chlorine behaves is based off of these valence electrons, right? So these ones are valence and the ones in here are core electrons. And so if I draw this out as the orbital notation, I have neon and then a 3s orbital and the p orbitals, and then I take and fill electrons in. So the 3s orbital has 2 electrons and the 3p orbital has 5. So 1, 2, 3, 4, 5. Okay, so this is the electron configuration for chlorine, right? Now, you guys know elements in this row like to gain an electron. Okay, and so if chlorine gains an electron, so I add that here, right? All of a sudden, this whole 3s and 3p shell are full. So chlorine Cl minus has an electron configuration the same as argon. Okay, so a lot of times these elements will try and fill their orbitals and get to this orbital or noble gas configuration. Okay, and the reason why is because if I have a full, an empty, or a half-filled shell, they're more stable. Okay, more stable means lower energy. So if my orbital's full, and by full, if I have an s orbital, means 2 electrons, empty means no electrons, or half full is 1 electron, these are lower in energy, okay? And this becomes more important when we get to the higher, not just S's, but higher ones, right? So here I have kind of another example. So I have calcium, and calcium's right here, okay? Calcium's noble gas configuration or electron configuration is argon 4s2. So here's argon 4s2, right? Now you guys know calcium right here, or these ones like to be +2s. So it likes to lose 2 electrons. And if it loses 2 electrons, it becomes more stable because now all of the 3s and 3p orbitals are full. So calcium 2+ has an electron configuration of argon. And so this is one of the reasons why atoms lose electrons, because if they lose electrons to be more stable or have lower energy. And so having that noble gas configuration is the most stable. Okay, so let's look at this one right here. So we have chromine with argon 4s2 3d5. Okay, and what happens if we take and lose 1 electron? And so the best way to do this I'm going to draw these out. I guess I should start at the beginning of this. Okay. So first off, I want to explain chromium, okay, or chromium. So chromium has argon, okay, and then it's right here. Okay, so if I were to follow the rules of filling this up, I would say 4s 1 2 3d 1 2 3 4. Okay, but remember, full, empty, or half filled shells are more stable. So what we're going to do with chromium is take this electron right here and move it up to that orbital. I just added this example in right before class, so I forgot I was going to describe it. Okay, so now if we move that electron up, it looks like this. So now all of my orbitals are half full, which makes this electronic orientation more stable. Okay, and so it's less energy for this electron to move up here and kind of hang out in this orbital than it is to have this 4s orbital full. Okay, because remember, these 4s and 3d orbitals are really, really close in energy. Okay, so now what if we take, so these are for chromium. Okay, this one's more stable. I think that yellow color is really hard to see. Let me find a blue. Okay, so now what happens if we lose an electron? So I wrote chromium 1+. So now I have to think, if I'm going to lose an electron, where is it going to be lost from? And remember argon, I forgot to put argon in all those. If I look at this, if I take an electron away from this one, then I'll have an orbital that has 4 electrons in it, right? But if I take the electron away from this one, then I can keep this 3d orbital half full, and this orbital goes away. So when I'm removing an electron, I'm going to remove it from this 4s orbital in order to keep this orbital half full. One, two, three, four, 5. Okay, so all those d orbitals are degenerate. They're the same energy, and there's 5 of them. So a few vocabulary words that I just wanted to kind of talk through in the last 5 minutes is talking about if electrons are paired or unpaired. Okay, so paired electrons mean that in one orbital, the box is all the way full, right? Unpaired electrons mean I have electrons that don't have a pair in orbitals, okay? And so magnetic things have unpaired electrons, which means if you take, like your refrigerator has unpaired electrons, if I put something else up on it that has unpaired electrons, it's going to stick. Okay, so magnetic things have unpaired electrons. Now there's different words. So paramagnetic means unpaired electrons and that it's magnetized. The words diamagnetic means all of the electrons are paired or non-magnetic. So if I have nitrogen, the electron configuration for nitrogen is 1s2, 2s2, 2p3. To determine if something's magnetic, whether it's paramagnetic or diamagnetic, I have to draw my boxes. And then I have to put my electrons in. 2, 2, 1, 2, 3. Okay, so if this nitrogen, is it paramagnetic or diamagnetic? Okay, so I have a few answers coming through. Okay, so it seems like everyone's saying, okay, it's paramagnetic, right? So right here, these are unpaired electrons. So if I have nitrogen, it's going to be magnetic, okay? If I have N3 minus, my electron configuration is 1s2, 2s2. Is N3 minus paramagnetic or diamagnetic? Okay, so here all of the boxes are full, right? The 1s2, 2s2, so this one is diamagnetic. And so anytime, like, if you have unpaired electrons or ones that are in their box by themselves, then it's going to be paramagnetic. If all the boxes are full, it's going to be diamagnetic, okay? So another example of this is zinc 2 plus. Okay, so here's zinc. And zinc has an electron configuration of argon. Let me go down here. 1, 2, 3, 4. So 4s2, 3d. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay. So zinc has this configuration of argon. And in the 4s orbital, there's 2 electrons. And in the 3d orbital, there's 10 electrons. Okay, so zinc itself, all of the orbitals are full, right? Now we're looking at zinc 2 plus. Zinc 2 plus is going to have the argon configuration. And now I need to remove 2 electrons. So I have 2 choices. I can remove one of these and one of these. Or I can remove both of these. Right? So I can decide where I remove these electrons. Now this says, why is zinc 2 diamagnetic, which means all paired electrons. So that means when I remove these electrons, it's better to remove them from this 4s orbital than it is to make this orbital less full. Okay, so removing the electrons, I'm removing these 4s electrons. And I'm left with 3d. So it's diamagnetic because I've removed those 4s electrons. Zinc is more stable because this electron configuration is completely full. Okay. So my time is up, you guys. If you have any questions, feel free to stay after, but practice these, go through the learning curves and just make sure you kind of understand how this works. Okay. And I will see you on Thursday.